probably 25 years ago, there was going to be hydrogen cars, hydrogen trucks, hydrogen planes. None of these have materialized. So what the hell happened?
Actually, if you go back even longer than you and I have been doing this, Mark, go back to the 1970s was the first kind of real hydrogen boom. So there was a huge wave around the year 2000. Jeremy Rifkin's book, Hydrogen Economy. And then, of course, all of that petered out. And then it came roaring back around 2017, 2020, 2021 was probably the peak of this cycle. It's just that hydrogen fundamentally is a really crappy fuel.
Welcome to Saving the World from Bad Ideas. I'm Mark Lynas, and I've had a few bad ideas in my time. I used to go out in the nighttime to destroy GMO crops, and I also opposed nuclear power. But then when I looked at the science, I found I got it wrong. Oops! I've learned the hard way that none of us are right all the time. So now I'm here to challenge the assumptions that we all too often take for granted, because the future depends on us getting it right. Hello and welcome to Saving the World from Bad Ideas. I'm here today with Michael Liebreich, who's the former Olympic skiing champion for, where is it? I can see this picture in the background of your video feed here, Michael. You've got to give us that first.
So I was on the British ski team. So usually when people hear I was at the Olympics, they say, "Did you win?" And I said, "Well, I was the highest placed management consultant." But that is actually me over my shoulder advertising cosmetics, suntan lotion.
Well, that's astonishing. I mean, you're the only Olympian I think I've probably ever spoken to, let alone the first on this podcast. So it's an inaugural moment for us, and welcome, especially for that. But also, you're the founder and CEO of Liebreich Associates, and you're the managing partner of Pragmatic Capital, and probably also well known for being the founder of what's now Bloomberg NEF, which I think stands for New Energy Finance, right?
That's right. So we were New Energy Finance, which was all sorts of fun and games because we didn't provide finance. We provided information to those who are involved in the finance world. And then that grew, and I sold it to Bloomberg. So it's now Bloomberg NEF, but it's the team that I created and trained. I haven't been involved there other than writing my essays a couple of times a year for, it's been some time now.
Well, welcome. And also, I think you're probably well known to our audience as co-host with Bryony Worthington of the amazing podcast Cleaning Up, which I highly recommend everyone to listen to once they've finished listening to all our podcasts here at Saving the World from Bad Ideas. And so we have to start with a bad idea, and there's no dispute about what we're going to talk about today. It's green hydrogen. And so the bad idea that you're going to debunk on this episode is the whole idea of green hydrogen. I'm really, really keen to get into this because I'm long enough in the tooth that I've been on the climate beat for enough time to remember how long hydrogen's been this huge buzzword. People are writing books about the coming hydrogen economy. Probably 25 years ago, there was going to be hydrogen cars, hydrogen trucks, hydrogen planes. None of these have materialized. So what the hell happened?
Well, so what we're looking at is actually, if you go back even longer than you and I have been doing this, Mark, go back to the 1970s was the first kind of real hydrogen boom. At that time, it was out of Japan because you had the oil shock. Japan, obviously not having fossil resources itself, suffered really badly from that, got a shock, and decided that hydrogen was going to be the answer. And we've seen just these waves of hype and excitement ever since, about every 20 years. So there was a huge wave around the year 2000. Jeremy Rifkin's book, Hydrogen Economy. And then, of course, all of that petered out. And we had about a decade when people didn't really talk about hydrogen very much. And then it came roaring back around 2017, 2020, 2021 was probably the peak of this cycle. It's just that hydrogen fundamentally is a really crappy fuel. It's just a very, very bad fuel. And so it doesn't matter how much money you throw at it, how hard you try, turning green hydrogen into a fuel is just a really, really, I wouldn't even say it's a difficult thing because that makes it sound like eventually you could solve it. It's just for all sorts of reasons of physics, thermodynamics, microeconomics, it's just never really going to be a thing.
Yeah, you are fighting thermodynamics, aren't you? Because it's a bit like using wood ash as a fuel instead of wood. It's like it's the product of combustion rather than the fuel that could actually deliver free. The thing is, it seems superficially, you take water, you put electricity into it, and you split it into hydrogen and oxygen. Well, what could be better? What could be a more promising fuel than that? But of course, it's the result of a combustion, so it's a long way thermodynamically down the ladder, isn't it?
Yeah, so I think there's a couple of, there's two buckets of problems. One is to produce it, you effectively have to reverse combustion. You have to take, water is, an oxygen molecule and two hydrogen molecules that have bonded with an enormous release of energy, and you have to do that backwards somehow. And so that's one problem. It's going to be expensive. And we can talk about why it's expensive, which is not just the electrolyzers. It's actually, it's a chemicals plant fed by electricity. And so it's going to remain pretty expensive. But the second bucket, which I think is equally important, is the one that a lot of people miss, which is even once you've got the hydrogen, you have to do things like compress it and move it around and then store it and then distribute it to wherever you actually need it. And then you have to use it. And you've got all these processors which are set up to use these perfect fuels, which are essentially fossil fuels or electricity. And then you have to re-engineer them to use this very difficult to handle, very kind of explosive and likes to combust and likes to escapey tiny molecule. And that just drives your costs up, up, up. And so could engineers get this stuff to work? Yes. And in a way, that's the tragedy, because they could get it to work. It just ends up that the things you need to do to make it work are just too expensive.
Yes, I mean, I guess it works in the lab, right? I mean, something I did in high school chemistry was split water using electrolysis and you get hydrogen. I mean, it's sort of, so I think that's probably people's level of understanding. You can easily make hydrogen, so why can't we use it as a clean fuel?
Right. And it's not just that you can make it, it's that you can move it around, right? You can put it in a pipeline. You can put it in a tank. You can compress it. You can put it in a bus. There are buses in London that are burning hydrogen or using hydrogen in a fuel cell. Fine. But the problem is the cost of doing those things. And in a way, I think that's what contributes to these waves of hype, is that it's actually, for an engineer, it's ferociously exciting stuff to work with, right? It's a really nice challenge. How do you run a train on hydrogen? And you think, oh, that's marvelous. What could be more interesting? Certainly more interesting than boring old electric train that's been around for 100 years plus. So it's very, very interesting for engineers to work on. And it's very poorly understood. I'm going to say this, I hate to say it, but anybody who doesn't have a really strong STEM background is not going to understand why things like compressing hydrogen to 700 atmospheres is a difficult thing, and then containing it, in some without leaking. Why is that a difficult thing? It's kind of obvious to people who've tried to actually do it in a lab environment or whatever. But then, as I say, for those people, it's just really exciting. Why not try? So you've got this kind of perfect, it's a perfect storm. And then you have obviously politicians who love it because it's a get out of jail free card, because they don't know how to solve climate change, but they can look all kind of whizzy and progressive by talking about hydrogen. And then there's a whole load of sort of incumbents who love to talk about it. Wink, wink, nudge, nudge. It's never going to happen. But if we talk about it enough, we can keep doing the stuff that makes us money. So there's kind of all sorts of reasons why this thing has captured everybody's imagination just time and again.
Exactly. And of course, your new fossil fuel plant is hydrogen ready. So that makes it okay to invest in from a climate perspective.
Yeah, well, you know what? My garage is Ferrari ready,
Well, at least it's not a Tesla. Look, you did a talk at, I think it was Imperial last year, where you really went in quite hard on some of these, on the kind of hydrogen dreamers, probably many of whom are in the audience. And one of the stats that really stood out for me was, I think it's like 100 million tons of hydrogen per year are produced. And so this is being used in chemicals and all sorts of industrial, probably making fertilizer as well, ammonia. But green hydrogen, so split from water using electrolysis, is less than 0.1% of that total 100 million tons, right?
That's right. So 150 years ago, Jules Verne, in the book about the Magic Island, he wrote, one of his characters said, in the future, we won't need coal because we'll be using, I think he said water, but I mean, he meant, meant hydrogen, obviously, split from water. And 150 years later, and 50 years after Japan went hydrogen crazy, and all these years after 60 countries have got hydrogen strategies as of about, they started doing that around 2017, 18, 19, 20. And still 0.1% of hydrogen that we use every day for fertilizers and petrochemicals, 0.1% is actually electrolysis. And by the way, that doesn't mean green electrolysis, because even those people who are electrolyzing are very often using a bit of green, but then a whole bunch of gas or coal to kind of keep the lights on, keep the electrolyzers running 24/7, which they need to do for economic reasons.
Which is quite astonishing. So green hydrogen can't even produce the hydrogen that we currently consume for all these other purposes. I mean, so how can it possibly? Well, look, I want to go back a bit, because I don't want to sound like I fully agree with you on all of this. I think I need to play devil's advocate to at least up to a point. Let me put something to you. You talk about cost a lot. If we'd been having a conversation about solar in the 1970s, it cost $10,000 a square inch or whatever it was. That's not a real figure, but it was a lot more expensive than it is now. You'd have been saying, presumably, that there'll never be a solar economy, and yet here we are, a long way towards an incredible sort of rollout of solar panels because it got that much cheaper. Can't hydrogen do the same?
So I love that question, because it's what I think in America they call a layup, and I am the guy who actually kind of worked out how cheap solar was going to get and founded New Energy Finance. I mean,
I didn't know that, by the way. This wasn't a setup.
Well, so it was, there were, at the time, frankly, solar was really minuscule and really expensive. And in fact, it was wind that was making most of the running in terms of the learning curve. But solar was clearly not far behind. And then by about 2009, 2010, I was all in on the learning curve for batteries. So I do learning curves. In fact, my very first job out of university was actually being a ski guide and a ski bum. But my second job was actually calculating learning curves for a consultancy based in London called Braxton Associates. And I've done them. I calculated them for even for things like printed circuit boards and stone quarrying. And everything we do has a learning curve related to, obviously, intellectual property learning and know-how and so on. But also, as we invest, we just build bigger machines, and we've built more roads and more equipment and so on, so that the costs come down. So I am, learning curves for me is almost a religion, right? This is what happens. The problem that you've got with green hydrogen is that if you look at the cost base of green hydrogen, only about 10% of it relates to the electrolyzer stack, which you could think of as being equivalent to, the solar panel, or in fact, frankly, the flat screen TV that, we're looking at, or the equivalent of a battery. The bit that is made in a high volume mass manufacturing plant, that's the electrolyzer stack. But for green hydrogen, you then have to put that into what is effectively a chemicals plant. About 3 or 4 times as much kit is nothing to do with the electrolyzer stack. It's things like compressors and tanks and pipes and a substation and these little things that you have to have called blast walls, because otherwise the whole thing's going to get is at risk, because it's such a nasty molecule to work with. These are big, complicated chemicals plants, right? And then the next thing you've got is that to drive them, unlike with a solar panel, you just bang it into a field and there it is, it produces electricity. This thing needs electricity in order to run, right? So what you end up with is about 10% of the cost is the electrolyzer, about 40% is heavy engineering, and another 40% is electricity. And by the way, as the other things get cheaper, the electricity bit gets more and more, a bigger and bigger proportion of the whole. So if you say, right, let's say green electricity in Europe right now, you'd be very lucky to produce it for less than €6 a kilo. And to put it in perspective, grey, dirty hydrogen that's used in a fertilizer plant made out of natural gas, that would cost maybe €1. So you've got to reduce, if you just want no carbon price, nothing, you need to reduce the cost, by a factor of 6. If you really think we're just going to make green hydrogen, we don't even need a carbon price, factor of 6, right? Where from? How? Do you think the electricity is going to get 6 times cheaper? Do you think that the compressor is going to get 6 times cheaper? Do you think that the substation is going to get 6 times cheaper? Of course not. Only the electrolyzer stack, frankly, could get 10 times cheaper, 20 times cheaper. It's just not going to help you. That €6 you could see it coming down to, I don't know, let's say €4. But can you see it getting down to one? Absolutely not. And even if you have a carbon price, it has to get down to about €1.5. Well, it's just not going to. Just not going to. As simple as that.
How cheap can electricity get? Let's say you're covering half of Saudi Arabia in solar panels, some of these hot deserts, let's say.
Well, so solar, before the inflation crisis, and sort of if you go back to just before the Russian invasion of Ukraine and so on, solar was pushing in Saudi Arabia. They were saying, I think it was $10, $11 per megawatt hour. Right. And but that was a little bit fake because there's all sorts of, cheap finance, free land, blah, blah, blah. So now we've had a bit of inflation, but then we'll have more learning. So, call it, I don't know, $15 or $20 per megawatt hour. Absolutely believable. But you've got a problem then because that's only 8 hours a day. Right. So then you're building this huge plant with all the stuff that I talked about, all of the electrical system, all of everything, except that you're only using it 1/3 of the time. So you're kind of caught between you're damned if you do, damned if you don't. If you go with just the cheap solar, you're only operating 8 hours a day. But if you then want to operate 24/7, you've then got to add a whole load of batteries to the solar. And so your electricity cost then has gone all the way back up again. And so neither way can you make really, really cheap green hydrogen.
I mean, I don't know anything about chemicals, but do you need to operate a plant 24/7 to get back the capital cost of it?
Well, that's not chemistry, that's economics, right? So in other words, if you just, for the same quantity of hydrogen, if you want to make it only operating 8 hours a day, you'll need 3 plants. And you've got another problem, which is chemistry, which is downstream, of course, because, what you're doing with the hydrogen, first of all, you could put it into a pipeline if there was a pipeline, but most people have realized that actually what you're going to do is make ammonia. And you'll either make ammonia for the local market or you'll export it, but you need to make ammonia. Well, guess what? An ammonia plant absolutely hates operating just 8 hours a day. Those are high temperature, high pressure plants, and they like to operate 24/7. So now what you've got is these sort of pulses of hydrogen. If you're only using solar, even if you've got the green hydrogen plant, operating cheaply 8 hours a day, which, by the way, they're much less efficient because you have to keep switching them off and on and they have to get up to speed and temperature and blah, 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 right? But even if you did that, now you've got to create buffer storage because for another 16 hours a day, you've got your fertilizer plant working, but you're not producing any hydrogen. So now you need lots of storage, you need compression, you're going to have to somehow make all that storage safe, et cetera, et cetera. So that's one of the things that happened around, 2020, 2021, when everybody got so super excited about this. They just didn't go through the engineering of, okay, you want to build an ammonia plant in Namibia. Lovely sun, fantastic. But how do you turn that into ammonia? What are the things that you need to do and how much do they cost? And when you do that, you find that, right now, you're not making any green hydrogen anywhere in the world at less than $4 per kilo. None of the plants on the drawing boards, not even in China right now, $4. Whereas the grey stuff from natural gas, I say in Europe, it's, let's say, €1.50, maybe a couple of euros, but depending on carbon price and so on. But, in most places, in the Gulf, in the US, in China, even, well, they would use black hydrogen. They're making hydrogen for $1 a kilo. And the green stuff is $4 a kilo. And, I could see it in the Gulf going down to 3, maybe, but it's still more expensive. It's more expensive. And that's just a huge problem.
That's only a 3 times differential. You said you were talking about a 10 times or six times. I mean,
in Europe, we're talking about €6 plays, 1.5. And by the way, 6 is already optimistic. If you look at the plants that are actually being built now in Europe, then they are the cost and there's some proper analysis by a Dutch organization called TNO that got anonymized data from actual projects, and it was 6 to 13 euros per kilo. And if I might, $1 a kilo or euro a kilo, $1 a kilo is a gargantuan problem because this is a commodity. when you're making ammonia for fertilizers, and you use the number, we can go through the arithmetic. Supposing you just say, right, let's take existing use of hydrogen and let's go to green hydrogen. We should start there, right? Before we start inventing other uses. 100 million tons of hydrogen being used this year. That is 100 billion kilos. So if you've got a $1 problem, right, you can make it for $1, but you're going to make it for, well, you haven't got a $1, but you've got more like at least, at the moment, a $3 problem. We'll come back to that. But for every dollar of cost difference, that's $100 billion per year that somebody has to find. It's as simple as that. But it's worse, because if you want somebody to build those plants, you can't just say, well, fine, here's $100 billion, go build the plants, because they'll say, doesn't work like that. You need to give me 15 years worth of 100 billion, right? Which is $1.5 trillion. $1.5 trillion for every dollar per kilo of cost problem. And as we know, we got a $3 problem, right? So that's a $4.5 trillion gap. That is the missing money. It's hydrogen's missing trillions, which I've written about. And so if you gave me $4.5 trillion, I could replace all the hydrogen we use today for the next 15 years, by the way. Not, straight after that, as soon as the 15 years is up, I'd switch those plants off because they're too expensive to run. But for 15 years, I would produce you nice, beautiful, clean, green hydrogen. But if there's no $4.5 trillion, I'm not getting out of bed.
Well, I don't know about you, but $4.5 trillion sounds like real money to me. But
it adds up, as they say, a trillion here, a trillion there. Soon you're talking real money.
That's where exactly. That's with a capital T, presumably.
Yes.
I mean,
T.
Yeah. I mean, there are big investment decisions being made into hydrogen, though. I mean, there's NEOM in Saudi Arabia. I think was that 4 gigawatts of solar, and I can't remember exactly how much hydrogen that's meant to produce. But that's a significant investment. I mean, are those people, are the Saudis entrepreneurs or whoever, or the king or the NBS, or are they all stupid? I mean, in putting this money there?
No, because they had an offtake from Air Products that said, we'll buy everything you can make.
What's an offtake?
An offtake. Okay. So when they were putting that together, they said, right, we're going to do this gargantuan project. It's a huge project. And it costs $8.5 billion. And they said, we're prepared to invest it, but we need a buyer. We need those 15 years of somebody to buy to offtake the resulting hydrogen. So Air Products, who had a very visionary CEO, signed up and said, yeah, absolutely, we're in, we'll do it. But, lots of press releases, and they got going building. So first of all, I believe that they were targeting $3 per kilo hydrogen when they signed all of that. And I don't quite know who was going to eat all those, those extra dollars. But what happened since then is that the costs went up. It's not been fully announced, but the costs now, I understand, are more like 4.5. But also, Air Products, basically, the board fired the CEO for signing that and other deals because there's nobody to buy it. Air Products sells industrial gases. So they thought, there'll be lots of people buying this, and those Europeans are kind of crazy, and don't know to what extent they had done their analysis, but they are unable to sign up off-takers. And so therefore, this has been for at least for the career of the chap who signed it, a catastrophic deal. And here's the thing. For all that this is a huge, huge project that cost $8.5 billion and so on, it would produce 1/500th of the hydrogen required to meet your challenge of replacing that 100 million tons per year. It's only 250,000. I think that's right.
Yeah, you said 0.22.
It's 0.2. So, yeah. Exactly. So 0.22. So if it was 0.2, it would be 1/500th. So it's a bit over 1/5. But so what you're saying is you've got these huge projects in the best, sunniest place in the world with the cheapest capital, with probably all sorts of freebies thrown at it, and you need 500 more of those projects to even replace existing hydrogen demand with green hydrogen. And I've never seen, I've been doing this for a long time, 20 years plus. I have never seen such a mismatch between, what policymakers and, the entire panoply of dreamers and grifters and just hopeful people, and they want so much from green hydrogen, and what it can deliver is so little.
I mean, let's just stick to the scale issue. So you'd need 500 of these 4 gigawatt projects, if you're looking at the solar model, just to cover the existing uses of hydrogen. If you were to expand those uses of hydrogen to do steel, I think you've said. Do you remember the figures off the top of your head, or I've got them written down?
Yeah, I haven't got them in front of me, but for each thing you want to do beyond that, you can basically assume that it's kind of 5 times all of the renewable energy that's ever needed. Not for each use case. If you put them all together, you put kind of shipping and aviation fuel and steel and a bit of long duration storage, and then you just kind of make really conservative assumptions about how much of that you might actually do with hydrogen, and you would need 5 times all of the wind and solar that's ever been installed, which, by the way, is now producing just under 20% of all electricity. So you're kind of saying, let's take all the world's electricity and just use it to make hydrogen, for fertilizers and petrochemicals and then a few of these new use cases. So the scale is just, it's unthinkable.
I mean, no one's told the Europeans this because they've just passed a law mandating that green hydrogen has to go into aviation fuel, right?
Yes, I mean, they've passed, there's a thing called RED 3, which actually covers putting hydrogen into not just aviation fuel, but also fertilizers and petrochemicals. And then, of course, part of the petrochemicals is the hydrogen that could go into aviation fuels. The aviation fuels alone is, I believe it's a percent or 1.5% by 2030. And when you do the numbers, it would actually drive up the costs of all flights in Europe by about 4% by 2030, because the resulting aviation fuel is 12 times as expensive as jet fuel. Not twice as expensive, not 4 times, not 5 times, not 6 times, 12 times as expensive. And so even if you only put in 1%, that alone drives up the cost of that fuel by 12%, right? Because you've got 1% times 12 plus 99% times 1, right? And you just do the maths. Just that teeny little bit of hydrogen aviation fuel, they call it RFNBO, renewable fuel of a non-biological origin, i.e. hydrogen-based and direct air capture-based, that would be enough to push up the cost of the fuel by 12 and the cost of your holiday flight by 4%. These are in percent, right? So, and what's amazing is, first of all, the people working on it, I don't believe understand the inflationary impact. I just don't think they understand it. And secondly, they don't seem to understand the political ramifications of going to every family that wants to fly off on a little holiday, 2030, that's going to cost you 4% more just to do this little tiny, teeny thing that has no pathway ever to being viable. And that's also an important factor, right? It's not like, oh, well, if you did a bit of that, then the costs will come down and suddenly we'll all be just like solar. It'll be really, really cheap. And, Europe will lead the world and we'll be exporting this technology. We'll be doing none of that.
And I mean, politically, you'd think it leaves the door open for populists who can just say this whole business is crap. They'd be right. And then they'd tear down the whole climate edifice, right? And destroy everything.
Yes, I mean, that's one of the things that motivates me, and to write something like just this piece about the pragmatic climate reset, is that if you really care about climate change, then don't do things that are manifestly stupid, because you'll get pushback, right? What you've got to do is do all the pragmatic, sensible things. By the way, there's this smorgasbord of things that won't cost 12 times as much and that will take a couple of decades. So why don't we just do those? But, this hydrogen stuff is like a brainworm. It gets into people's heads. It gets, by the way, also into people's careers and into their political capital. And then they can't just say, you know what? Actually, we've now run the numbers, and that ghastly Liebreich chap, he's very annoying, but he's kind of right. So let's stop. They just find it very difficult to do that.
And so presumably if green hydrogen can't even decarbonize hydrogen, I mean, simply because of the expense, then there won't ever be syn fuels made from direct air capture, CO2 mixed with green hydrogen, right? That's never going to happen.
Well, so there will be syn fuels because there are, or there could easily be, because there are very, very rich people with supercars, and they want their cars to do, to make the right, vroom, vroom, pop, pop noises. And, I was just watching a video yesterday, as it happens, about there's a Hyundai, I think it's the Ioniq N5, drag racing against a Lamborghini, a Porsche, a Maserati, and a Jaguar. And it's basically a race for second place. This cheap electric supercar, I mean, it's just just looks like a normal car, frankly. It looks like the sort of thing that you do, school run in. And it leaves them absolutely for standing, but it sounds like a vacuum cleaner. And so, of course, there are people who would say, no, I still want the Lamborghini, and I want the cars are supposed to sound like cars. So, okay, well, they are the sort of people, frankly, with, brains small enough and wallets big enough to buy syn fuels. And, Porsche has got its project over in, I think it's in Peru or Chile, where it's making a few, and it's incredibly expensive. So for the average person, and, when you get German politicians who say, we must have this thing they call Technologie-Offenheit, technology openness, because maybe the way to allow, Herr und Frau Schmidt to continue to drive their existing car and not to have to scrap it will be to do syn fuels, to do e-fuels. I can guarantee you, Herr und Frau Schmidt, if you're listening, I'm so sorry. Use your car, enjoy it, get it to the end of its life, sell it for scrap or sell it into the secondhand market, and buy an electric, because you're never going to be driving on syn fuels. You're never going to be driving on e-fuels. I'm really sorry. You've been misled.
And the electric thing, that goes for everything that was supposedly going to be hydrogen. Trucks, for example, were going to be hydrogen because it was too expensive. It was too heavy to run a truck with sufficient batteries, right?
Well, so trucks, I've got to confess here, I'm going to trade my book, because I did the analysis 5 years ago. And as a result of that, I founded something called Pragmatic, which is a charging provider, pan-European, for big rigs, for trucks, 40-ton plus trucks. And the core thought is, look, the truck is more expensive than diesel, but the fuel and the maintenance is less expensive. So as long as you do enough kilometers during the course of a year, then the initial cost of the truck is sort of irrelevant, because it gets amortized over all these kilometers. And what matters is fuel and maintenance. And so there's a break even where you can provide an electric truck, green electric truck, if you've got green electricity, cheaper than diesel, without subsidies today. And that's what we're doing. And of course, people said, it couldn't possibly work because the batteries are too heavy. Because to drive a sort of 500 mile truck, what you've got is 5 tons of batteries. Now, obviously, eventually that'll become 4 tons and 3 tons, because batteries get better and better. But nevertheless, take the figure of 5 tons. Well, guess what you're doing? You're removing the engine, you're removing the gearbox, you're removing the differential, you're removing the fuel tank, you're removing the exhaust system, you're removing most of the stuff that protects the driver from being rattled into pieces during their shift driving. So it turns out that the battery truck is, a couple of tons heavier. But here's another thing, though. So, 2 tons is not trivial. 2 other factors, though. First of all, very few loads actually push the weight limit on the truck. Think of all those Amazon boxes. They're full of air, right? They're not full of mineral water. So if you're trucking mineral water or beer, Herr und Frau Schmidt, your beer being trucked around Europe, that truck is probably at the maximum weight limit. But all the ones with parcels for the post office or furniture or, almost like you name it, food other than really densely packed, heavy food, those are limited by volume, not by weight. And the final thing is, when you drive a normal truck uphill, and by the way, it slows down, which means that you're paying your driver's salary whilst they drive up the hill at 50, 60, 70 kilometers an hour, being overtaken by our electric trucks, which can drive at 90 kilometers an hour because they've got enough torque to do that. When you go down the other side, all the energy you used for the diesel truck, actually you get back in regenerative braking with the electric truck. Now, hydrogen has to compete into that matrix where electric trucks are going to be cheaper than diesel with subsidies now. And then you've got a much more expensive truck with much higher cost maintenance, and the battery is too small to do all of that regenerative braking thing. And by the way, its range is not even better because the hydrogen is so bulky that hydrogen truck is full of hydrogen tanks. But of course, your engineers then say, yes, but, Herr Liebreich, our wonderful engineers can use liquid hydrogen because we're Daimler. And the Swedish ones, I can't do the accent, will say, well, we'll do hydrogen, liquid hydrogen as well. Well, that's great. Now you've got to make the liquid hydrogen, which wastes 40% more of its energy content beyond making the hydrogen. And I got bad news for you. You can't drive it through the Channel Tunnel because it's off-gassing hydrogen all the time. As the heat goes into the liquid hydrogen, you're sitting under a plume of hydrogen. Try explaining that to Le Shuttle.
This is another obstacle, to say the least, right?
So then, if you can't drive through the tunnel, yes. So the logistics of trying to do a liquid hydrogen truck, which might have a longer range, are absolutely ferocious. And actually, there's a third reason why the electric wins, which is that, at least in Europe, you've got the working time directive. After 4.5 hours driving, that driver has to stop for 45 minutes and can then drive again for 4.5 hours, and then has to call it a day. Well, guess what? If you can charge the truck in 45 minutes for as far as that driver has driven for the first 4.5 hours, which is about 250 miles, 350 kilometers, 400 kilometers, something like that. If you can then have a rapid charger right there, that truck essentially is autonomous, can drive anywhere. There's a meta point here, which is instead of running around with a hydrogen hammer looking for a nail, say, well, maybe there's this use case. Instead of that, this is what drove me to do the hydrogen ladder, which you might have come across, which is think about each use case and ask, how would you decarbonize that? Is hydrogen the best way to decarbonize it? Because if hydrogen comes second in every single use case, it effectively has no market. And that's what happens below the sort of row A, row B, row A is where we use hydrogen already, the 100 million tons, and row B is a few things that are really difficult to electrify directly. But everything you can electrify directly, basically hydrogen loses.
And so I did want to talk about how you can ship hydrogen, right? We have great big super tankers that take LNG, liquefied natural gas, around the world. Lots of them dock in Europe, and that replaces most of Russian gas, although some of the LNG comes from Russia, but that's a different story. But anyway, like in terms of the physics of this, you can liquefy, I guess that's mostly methane, and put it onto super tankers and move it. Can't you do the same when you liquefy hydrogen?
Well, so this is one of the things that in that lecture that you referred to earlier that I went into in some detail, because you do get a lot of people saying, well, we did it with LNG, so we'll do it with hydrogen. And that's a bit like saying, well, we broke the sound barrier, so we're going to break the light barrier too. And these are just physically fundamentally different things. And where it starts is just density. So, I was berated. I spoke at the Global Hydrogen Congress, World Hydrogen Congress in, I think, 2023. And I tried to explain some of this, and people came up to me afterwards. One chap I remember very clearly who was livid that I said you can't ship liquid hydrogen. And I asked him, I said, well, do you know the density of hydrogen? And it turned out that he was a politics grad. So he said no. And I said, well, it's 71 kilos per cubic meter, right? Since you're a politics grad, water, I said to him, water is 1,000 kilos and LNG is about 450 and hydrogen is 71. What this means is,
I'm a politics grad as well, so you need to explain why.
Okay, well, I'll slow down and use short words for you there, Mark. No, so what it means is that although hydrogen gets a lot of energy density, each kilo carries 3 times as much energy as LNG, but it's sort of 9 times less dense, more bulky. So that if you do volumetric energy density, not gravimetric, not energy density per kilo, but energy density per cubic meter, then you end up with needing 3 ships for every LNG ship. And ships are volume constrained. They have to get through things like the Panama Canal and the Suez Canal and so on. So, and they've got, certain dimensions that you can build. So you basically need 300, even if everything else was solved, you'd need 3 hydrogen ships for every LNG ship to deliver the same amount of energy. But you've got far more problems, because you're going to start with hydrogen and you're going to liquefy it. And it turns out that that's an absolute bear of a process. It's horrible, because hydrogen does this weird thing that when you compress it, it gets cold. It has what's called a negative Joule-Thomson coefficient. So when you take natural gas, what you do is you can compress it and then remove the heat. And then you can compress it some more and remove the heat. With hydrogen, it sort of goes the other way around. You compress it, it gets colder. How do you remove the heat? Because when you're trying to liquefy, that's what you're trying to do, suck the heat out. So you have these really complex processes.
So, Michael, you said isotopes there. Did you mean isotopes like deuterium and tritium?
Sorry, did I say isotopes? I meant isomers. So what happens is, get very technical, but the protons in the hydrogen atom can spin either left or right, and they can flip. And so what happens is, if you cool them down, then more of them want to be one versus the other. And as they change, they give out a teeny tiny bit of energy, but it's enough to regasify the hydrogen from the liquid state. So there you go. That's, I don't want to say it's a chemistry lesson, because somebody's going to write in and say I'm wrong, but that's the best I can do. So this is just a really, really complicated process. And by the way, everything has to be made out of the highest grade steels, or the right grade steels for hydrogen, because otherwise they go brittle and just snap. And the hydrogen is trying to escape from every screw thread you've got. It's probably got enough of a tiny little gap to let the hydrogen out, which doesn't happen with the methane. So you've got to, but when you liquefy, it takes about 40% of the energy of the hydrogen to liquefy it. Now, that can be improved a bit, but you know what? They've been doing this for a long time and they haven't managed it. So, maybe you can halve that. Theoretically, you can't go much below that. But what it means is that you're probably going to have to start with 4 or 5 ships worth of hydrogen to get 3 ships full. And then you start sailing, and the heat comes in because you're sailing across from, Saudi Arabia or UAE or wherever, nice and hot. And so the sun beats down on your ship and the hydrogen turns back to gas, and you can use a little bit of it in the engines. But most of it, you just have to, you can either lose, which is a greenhouse gas, incredibly powerful, or indirect, but very powerful, or you can flare. So you can steam along under an invisible flame of hydrogen. And what you end up arriving at the destination with is 2.5 ships worth. You started with 5, liquefied it, stuck it in the ship, sailed for 20 days or wherever, and then you've arrived and you've only got 2.5 ships worth. And how can I put it? This is, of course, engineers are like, oh my God, this is the most interesting thing I could possibly work on, right? Because they love this stuff. But anybody with a spreadsheet or a pencil and the back of an envelope is going to say, not going to happen.
Yeah, I mean, as a politics grad, even I'm beginning to get the idea here. But I didn't actually know that hydrogen was a greenhouse gas. I mean, you said indirect. Explain that quickly.
So what happens is, I know you've done a lot of work and incredibly good work on methane, on fugitive methane emissions. So methane is a very powerful greenhouse gas. It's something like, I think it's, It's 22 times worse than CO2 per kilo on a 100-year basis, but 80 times, so much worse over the next 20 years, because it degrades in the atmosphere. So when methane escapes, natural methane, frankly, from decaying biomass or fugitive methane and coal bed methane and so on, it's a very, very bad greenhouse gas, but it does decay in the atmosphere. And the way it does that is by capturing, I think it's a photon of energy, and then that sort of breaks the CH4, then kind of goes off and becomes ultimately CO2 and some water. So the hydrogen goes into water. Now, by the way, I may be good at this stuff, but I'm not a particularly good atmospheric chemist. But what happens is the hydrogen scours, because there's some other molecules or some ions involved, the hydrogen preferentially scours those. So the methane, although hydrogen doesn't capture the radiation, it leaves the methane in the atmosphere for longer, and the methane therefore captures more radiation, and we get more of a greenhouse effect.
Hydroxyl radicals, I think they are.
Hydroxyl radicals. Bingo. They did teach you something in politics school.
I was just pretending to be completely thick, obviously. Listen, I think we've got through most of the hydrogen stuff I want to talk about. I mean, you mentioned that hydrogen's only going to ever be used in homeopathic amounts, which triggered me because I hate homeopathy. But
can I let me just qualify a little, right? What I said was the homeopathic, that would be the amount that would be shipped as liquid hydrogen. You can do it, but it's homeopathic. They did one ship from Australia to Japan. It only burst into flames once, but it did arrive with some hydrogen and so on. So, there are some use cases where you might see green hydrogen, right? And that nowhere enough to make it a hydrogen economy or even to seriously dent the 1 million, the 100 million tons. But I just want to be very clear, because I don't want to then be proven wrong, because there are a couple of edge cases where it works. And I'll give you 3, if I might. One is, there are places we use hydrogen which are distributed, out in the economy. Very, very few. There's the odd lab where we use hydrogen, but there's also hydrogen, it turns out, is a very, very good thermal conductor, but reduces but without creating lots of drag within generators. So really, really good generators, they actually fill them with hydrogen with no oxygen, because otherwise they go bang, which they do occasionally. South Africa had one of those. But if you fill them with pure hydrogen, then you can run your generator sort of faster with lower heat losses and lower turning resistance. Now, if you wanted to make that, right now you'll deliver that via a tube trailer, very expensive, and you might make that on site. So that's use case 1, is on-site manufacture, where you really need hydrogen out in the economy. Second one, and Henrik Stiesdal, the great inventor of the wind turbine, of the modern wind turbine, is doing this in Denmark, where you're making biogas, anaerobic digestion. You produce some CO2, which right now you either sell to grow tomatoes or for a little bit into Coca-Cola, but fundamentally it's just released. Well, a small amount of local hydrogen, you could then produce a bit more biogas, a bit more biomethane. And it's just possible that he can get the economics to work on that. And the third use case is in a country or a region, a location, where you've got very cheap renewables and expensive natural gas and lots of farmers. You might be able to get the economics of green ammonia, green fertilizer to work. Now, you're thinking of places like China, India, Brazil, cheap renewables, expensive gas, therefore expensive fertilizer, and local demand where, you don't have to ship, you don't have to do all that complicated stuff shipping around the world. So those are the use cases, I think, where it might work. But by the way, even in those use cases, you'd be much, much better advised, if you care about the climate, you'd be much better advised to use the electricity directly. You'll do much better for the climate. The cleanest kilo of green hydrogen is the kilo you never make.
And just to reassure people, you're not saying this because you're some kind of degenerate climate skeptic, right?
No, not at all. The opposite. So if you've got a kilowatt hour of green electricity and you say, oh my God, I'm really, really worried about the climate and so on, what would you do? Well, first of all, push coal off the grid, which of course in the UK we've done, but elsewhere we've not. Push coal off the grid. Second thing you would do is put it in a heat pump. And the third thing you would do is put it in an EV. And you will do 2 to 9 times more for the climate, which means, by the way, that even if you have a huge curtailment, even if you can only use half of it, it's still better and cheaper to do those things than it is to start trying to make green hydrogen, which is why all this stuff about, using surplus electricity, forget it. You're never going to get the economics to work, and it would be bad for the climate. But of course, we're obsessed with it. I think the government in the UK is doing yet another consultation on blending hydrogen into the gas grid. I call that the stupidest idea from Stupidville, because even if somebody foolish enough to invest would do it, it's bad for the climate versus just dump the electricity locally, on people with electric cars and heat pumps, put a big smile on their face, drive the transition forwards at speed with political support, and it's better for the climate in every possible way.
Yeah, my electricity provider gives me free electricity every now and then when they've got a surplus, and I rush around, I plug in the cars, I rush around switching everything on. I love it, even though, it's probably only pennies, but it's somehow feels good to use curtailed electricity.
Absolutely, but that same, the problem is that green electricity might be coming from wind farms, which, when it's really, really windy, are being switched off. And our regulatory environment is such that we actually pay the wind farm to switch off rather than maybe paying you to use it, or at least dumping it for free. And then, of course, so what we do is pay in Scotland and the north, we pay the wind farm to switch off. And then down in the south, we pay somebody else who's probably a mate of the person with the wind farm, if not the same person. We pay them to generate using gas. I mean, it's completely bonkers. And thinking that the solution to that is anything to do with green hydrogen is, I'm sorry, but as systems thinking goes, it's really pitiful.
And so there's not much left of your green hydrogen Swiss Army knife, not many blades or pruning saws or little scissors or anything that, like the Swiss Army knife metaphor, which I think you've said was actually quite apt, was originally this idea that green hydrogen could slot into all of these different things and decarbonize them. And actually it's the worst option in pretty much all of them as far as we can see so far.
Yeah, so the Swiss Army knife analogy, I actually think I borrowed or stole.
Did you coin it?
No, I didn't coin it. I'll be honest. There's a guy called Paul Martin who's an exceptionally good chemist. And, he was calling it the Swiss Army knife. And it stuck somewhere. I thought I invented it, but I went back in time and I looked at posts that I'd liked and so on. And it's definitely from Paul. So, Paul, I've given you credit many times. I'll do it again on here. But it is the perfect analogy. Because I never said, oh, it's the Swiss Army knife. I never fell for that kind of hydrogen economy, Swiss Army knife sort of hype cycle, maybe for about 3 weeks in 2003. But the reason it's such a good analogy is that there's all these things you can do with a Swiss Army knife. You can, prune your apple tree, or cut your hair, or spread butter on your bread, or, use those little tweezers. I mean, you never do any of that, right? What you do with the Swiss Army knife, if you have a horse, you might get a stone out of its hoof. Even that I doubt. I use mine to open a bottle of wine on a camping trip. And that's about it. And the reason is there's almost always something cheaper, safer, and more convenient. Cheaper, safer, more convenient. Just really simple summary of why hydrogen is the Swiss Army knife of energy, because there's almost always something cheaper, safer, more convenient. Unless it's a feedstock, right? Unless you need it for hydrocracking or hydrogenation or fertilizer manufacture. And at that point, there's nothing else that does the job. But every time you start looking at other use cases, you're going to find something that's cheaper, safer, more convenient, or, with maybe the exception of a few things around long duration storage, or maybe a little bit of, what Henrik Stiesdal is doing of, adding it into biogas. But again, that's as a feedstock use. So it's Swiss Army knife. It is the Swiss Army knife of energy. But before you give up your career to chase the dream, understand that means that we'll probably almost never use it.
Yeah, because Swiss Army knives are shit. I mean, I was trying to take the top off a plug the other day, and I could only find the Swiss Army knife, not the screwdriver, and it took they're the shit bottle openers, shit.
Yeah, you've got that. You got the bottle opener with a little screwdriver on the end, and then you try and use it, and it flips shut on your finger.
It does, but I'm delighted you take bottles of wine camping, though. I mean, that is really reassuring that you're living the good life, Michael. Before we move off hydrogen altogether, I suppose we should talk about what the alternatives are. Because, all right, you've debunked hydrogen, right? So how are we going to decarbonize steel, aviation, shipping, all the things which are the sort of so-called hard-to-abate sectors?
Well, so first of all, we've framed this as green hydrogen. We're not going to get off hydrogen, and we are going to need to do clean hydrogen. And just that 100 million tons per year of hydrogen that we use generates about 2.5%, I think it's 2.3% a year or two ago, of all the emissions produced by our human activities. And so we need to deal with that. What I would say is it's not the most urgent of problems. If you look at things like domestic heating or land transport, those trucks that we talked about, then there are things that you could, that you could move very quickly on that are more substantial. And so, but we do need to decarbonize the top of the ladder. And everything that I've looked at suggests that the way to do that is essentially going to be fossil hydrogen with carbon capture, which is an absolute, it's been demonized by fans of renewables and, of course, the whole green hydrogen brigade. They say it's impossible. But, and it's not from an engineering perspective. Let's be absolutely clear. You can do this thing called autothermal reforming. So you can take natural gas, and when we've tried to do carbon capture in the past, what we've tended to do is burn gas or coal for that matter, and then try and get the carbon dioxide out of the exhaust. And that's really a hard way to do carbon capture. And the way that they're suggesting doing blue hydrogen, so clean hydrogen from methane, from natural gas, is kind of analogous. You use this thing called steam methane reforming, and it's just very difficult to capture all of the CO2. So it's been tried a few times. It's a tough process. It tends not to capture enough. It tends to break down and not work and so on. But there are other processes like autothermal reforming, or you've got to love the creativity of the hydrogen crowd. Turquoise, another color, hydrogen, which is using a process called pyrolysis, where you take your methane, you take your natural gas, which is methane for the chemists among us, CH4, and what you do is essentially get the carbon out as solid, so not as CO2, which is gas, but a solid carbon, which you can then bury. You can call it reverse coal mining. So there are ways of doing hydrogen from fossils that is clean, but as society, we would have to make some pretty tough choices to do it right. So as soon as you let some methane, some natural gas escape, you've got a problem. As soon as you don't capture all of the carbon, solid or CO2, if you're doing it that way, as soon as you don't capture it all, you've got a problem. But they're engineering problems. They will cost money. It's more expensive to do it right than not to do it right. But the challenge is trivial compared to changing the laws of physics so that green hydrogen becomes cheap enough to do, gets down to the kind of $2 a kilo level that you could do blue hydrogen and maybe turquoise hydrogen. So we can have clean hydrogen. I just think that the vast bulk of it will end up being from fossil rather than green.
So nuclear any good? I mean, there's high temperature nuclear reactors that can produce hydrogen, at least at least physically. Economically, I don't know, but you tell me.
Again, the engineer in me is so excited about, we get to, so first of all, clearly you can make electrolytic hydrogen, go back to those wonderful colors. That's called pink hydrogen, where you just take nuclear power and you make hydrogen. And the problem is, so that's pink hydrogen. Of course, you can do that. The problem is you're committing a crime against thermodynamics. You're taking electricity, the highest value thing that you can do, and it's a kind of a wonderful source of electricity. If you've bothered to build nuclear and it's coming out, I don't need to tell you this because you've had your epiphany. You love nuclear. You've got 24/7 or nearly 24/7 nuclear power. What would you do? Waste, a third or 40% of it, turning it into a fuel, which wastes another 50% of it, burning to get back to electricity. So you're tearing up £10 notes or $10 bills, $100 bills, frankly, but you're also destroying this thing that engineers and physicists talk about and chemists called exergy, the ability to do work. If you give me one joule, 1 kilowatt hour of energy, then it's not all equal. High temperature heat is worth much more than low temperature heat. Electricity is worth much more than a fuel. Lasers are worth most of all. One kilowatt hour of a laser you can do really clever things with. So what we're doing when we make pink hydrogen is taking very high value energy in the form of electricity and just wasting most of it. Now, you can take high temperature heat out of that nuclear reactor and you can use it to help the process of making hydrogen. You can decompose hydrogen directly, or you can use it to reduce the amount of electricity you need. Fantastic. But you're wasting high quality heat. You're destroying exergy. You're committing a crime against thermodynamics by doing that. So I'm afraid, how can I put it? If I was on whatever it is, Dragon's Den, I'd be, out.
Well, you mentioned Drag Race earlier, and that's the only Drag Race I've ever watched is RuPaul. There isn't much discussion of hydrogen there. It's mostly about dressmaking.
Well, there wasn't much hydrogen used making it either, but a lot of electricity.
That's true, which is, of course, the highest grade. So nuclear overall, I mean, your co-host Bryony Worthington is an even bigger fan than I am. And, do you have arguments about the viability of nuclear for decarbonising electricity production?
So we do have, I don't know, arguments is a big word. I respect my esteemed co-host on Cleaning Up much too much to have a proper argument. We do have discussions. And I think, look, I studied nuclear engineering, and I would love for there to be an easy way of building cheap nuclear power stations. I'm not that worried about, I think safety can be managed. And as well as anybody, the statistics of how many people have actually died, even in those ghastly accidents in, even Chernobyl, the worst accident with the greatest loss of life, it's measured in thousands, where coal and the pollution impacts of coal is killing, far, far more. And that's without even the climate impacts. So I'm a big fan of nuclear, but I have just got economic scar tissue from trying to work out whether you could do it, how you would do it cheaply. And I'm just not seeing it. I'm not seeing it with gigawatt scale reactors. I'm not seeing it with small modular reactors. I'm not seeing it even, I hate to say, we're told, they can do it cheaply in China. They can do it cheaply in Asia. Well, there are so many places that they can, but they almost certainly are hiding costs. And how can I put it? If it was that easy and that cheap, then why is nuclear in China losing market share to wind and solar? Because it is. They're growing it as fast as they can. And the wind and solar is absolutely like that Hyundai N5. It's just leaving the nuclear build in the dust. Absolutely in the dust, even in China, where they're trying to go as fast as they can.
Wow. Well, here at Saving the World from Bad Ideas, I think we're pragmatists. I mean, I'm with Deng Xiaoping. Speaking of China, I don't care whether the cat's black or white, as long as it catches mice. Whether he said that or not, I don't know. But come on, tell us, what's the pragmatic way? You've talked about a pragmatic climate reset. You've mentioned that you've written an essay on this. What's the pragmatic way through all of this endlessly confusing morass of competing ideas?
As we record this, maybe not as it comes out, we are halfway through the release of I wrote a two-parter called the Pragmatic Climate Reset for Bloomberg, and it's also gone out. The first part's already gone out on Cleaning Up. And the first part is really to say, look, for all that we want to go incredibly fast with climate action, trying to go too fast, 1.5 degrees, which implies decarbonisation, reducing emissions by 50% by 2030. The problem with going too fast is it's almost like, to use my drag racing analogy, we've flooded the engine. We've tried to do things too fast. It's been a good exercise. We've learned a lot. We've redlined how fast the economy can switch, but really we've started to do some very, very stupid things, and we've got political pushback, obviously in the US, but really across Europe, we're seeing this kind of consensus for rapid action, super rapid action break. So the first thing is, think like a tortoise, not like a hare. Pragmatically, what we really need to do is, if we're going to, we've got growth in energy demand is a beautiful thing. I don't mean primary energy demand as the IEA defines it, which is, of course, energy supply. I don't care about that. Demand, people traveling more to see their grandma, or having a warmer house, or colder beer, or being able to drop their kids off at school, all those things, that's demand for energy services. I want to see that grow, because that's human progress, right? More MRI scanners across everywhere, global south, everywhere, and so on. So we want to see energy demand, real demand, grow. But the pragmatic approach is to say, what we want to see is clean energy grow faster. So the first thing is stop demonizing fossil fuels, because so far the clean options can't actually replace them. They simply can't grow fast enough to replace them. They will be able to over time, but they can't in the next few years. So think like a tortoise, not like a hare, and don't worry about the last 5 or 10%. To put this in a UK context, for instance, we've got Clean Power 2030. Well, the thing is, meanwhile, we don't really have a plan to decarbonize heating, to decarbonize transportation, and to decarbonize most of industry, which could be done pretty easily and affordably with existing technologies. So don't worry about the hydrogen for long duration storage or the CCS retrofitted to existing power stations. These are really, really difficult things to do. And yet you got Rachel Reeves, the Chancellor, allocating tens of billions of pounds to them when we don't have a plan for electrification of heating, transport, and most of the simple stuff in industry. So the pragmatism says, do you know what? There's this smorgasbord of relatively affordable things that's right in front of us. Let's just do that, and let's do it, more and more each year. Let's start where we are, and let's grow like that drag race, right? You come off the line and you accelerate, and you're still accelerating when you hit the finish line. When you finish your quarter mile, you're still accelerating, right? And that's the sort of thinking that we need. Come off the start line where we are today, keep accelerating, do the obvious things that are right in front of our noses. And in the end, frankly, Mark, by the time we finish our careers, you and me, if we've decarbonized 90%, maybe 95%, maybe even only 85% of the economy, I think we will sit there in whatever year it is, 2045, 2055, 2060, I'll be 97, you'll be younger than me, better looking too, but we'll be pretty happy. We'll be pretty happy at that point. We'll have done a good job.
I'll take that.
Exactly.
I'll definitely
That's pragmatic.
Yeah. I mean, someone else I think can worry about the final 5 to 10% because they will have invented new things and they'll be smarter than we are anyways, as we currently said.
Exactly. And if you think about, for instance, the Climate Change Committee's work, where they sort of mark the homework, say, are we on track for 2050 net zero? I have to be honest, there's a part of me that says, do you know what? I would go for 90%. And if somebody said, no, it says in the law that you have to do 100, I say, no, I'm still targeting 100%, but there's 10% that we know will come from stuff that's not been invented yet. 2050 is 25 years into the future. I'm not going to put all the policies into place today without knowing the technologies, the learning rates. Liebreich will end up being wrong. Hydrogen is marvelous. The laws of physics did change after all. And that last 10% is going to fall to something we've never thought of. Quantum computing, something, who knows? And I don't think we should be holding ourselves to ransom for that last 10%. I just think it's unwise, and it's created a lot of that political pushback that we're suffering from.
Yeah, I guess perhaps this is a result of climate modeling and the kind of, the focus on 1.5, because it does mean obviously we're giving up on 1.5 because it's almost already in the rearview mirror, but, you have to make everything add up with these scenarios, don't you? You have to get down to zero, you have to go below zero, you've got to do it by 2070 something in order to get to 1.7 or, so yeah, there's this kind of focus on like being able to predict the entire global economy throughout all the way up to 2100. And, rather than just saying, hey, shit's going to get invented, which doesn't yet exist.
Well, absolutely. And, the whole scenario sort of community, what they've got is these models that are very resource intensive to run. So they run them for 100%, net zero, and they don't allow them to say there's 10% is just, whatever. And therefore they reach for whatever technology that exists that they can envisage and that they've characterized today. And they say, well, it's direct air capture, carbon capture and storage, but we can only do so much with biogenic carbon. So it reaches for direct air capture and it reaches for things like hydrogen because they don't allow it to they don't allow the model to turn around and go, well, look, I'm really sorry, but you told me society would only ever put up with a $250 carbon price. And so the last 10%, I'm just going to leave for the moment and we'll have to come back to it. The model can't say that. The model has to, if you say get to 100, the model gets to 100. And, there's other modelers, you also got the whole the whole story of RCP 8.5, these extreme climate scenarios, why did they happen? Because the models, when they were looking at 2100, they said, well, by that time, all the oil has run out. So what are we going to do in a situation where society is wealthy and the oil's run out? We're clearly going to do, what Nazi Germany did and what South Africa under apartheid did. We're going to make our fuel from coal. And they used coal as a filler for all of the transport associated with a wealthy world. They didn't let the model turn around and say, yeah, but at that point, half all the coastal areas will be underwater, and therefore we won't be doing any of that, really. It's an internally inconsistent scenario. And actually, as Justin Ritchie and Dalatabadi in 2017 found, there isn't even enough coal if you wanted to do that. Literally is not enough coal. So the models have drawn us into these sort of cul-de-sacs of either absurd scenarios, which were never realistic, but also into absurd solutions, which were never realistic. And and that, how can I put it? That is the opposite of pragmatic.
Mm-hmm. But if we take this pragmatic approach, you look at the rates of the deployment of clean energy, we're probably, I think you've projected going to hit zero fossil fuels in. Well, this was a very back of the envelope model, wasn't it? But what's your kind of give us where we get to if you think like a tortoise.
Okay,
like a hare.
So let me talk you through my tortoise hare sort of model, which I created using 4 lines of a spreadsheet. And we've spent 10 years, as I say, I think it was a useful exercise, just trying to figure out how would you get to net zero, because before Paris mentioned 1.5 degrees, and the IPCC said, well, if you want 1.5 degrees, you need to get to net zero by 2050. And then everybody started to, look at decarbonizing everything if it was possible. Before then, we were aiming for things like 80% decarbonization, which of course for most people is like, well, that's fine because I'm in the 20%. I can still fly to New York because that's in the 20%. I can still make my hydrogen-based fertilizer using natural gas because I'm in the 20% and so on. When you go to net zero, it shines a light on all of those things, and that's good, right? But what it means is the IPCC report in 2018, SR15, showed that what you actually need to do is get 50% off emissions, so 50% off fossil fuels by 2030. So paraphrasing that, we have to walk away from, decommission, destroy, strand 50% of our fossil energy infrastructure. So, of course, it was never going to happen. And the other thing is, again, in that IPCC report, the marginal carbon price that it came up with, published it, and nobody noticed. Nobody took any notice. The marginal carbon price for 2030 that it came up with was not $225, which was what you need if you're going to head for 2 degrees of warming, but $6,050, which is the sort of number you need to do crazy hydrogen stuff, right? So that's the hare. My 4-line model, all I said was, let's say the economy keeps growing at 3.3%, as it has done for a couple of decades. Let's assume that energy efficiency keeps going at about 1.3%, real energy efficiency. So tons of steel for the same amount of energy input or whatever. So real efficiency on the demand side. So that means that human progress continues and demand for energy services grows at 2% per year. Now, the model that I built, I didn't say how it happens. I didn't look at policy. I didn't look at any technologies. I just said, what happens if clean energy, not just renewables, but clean energy, so that is renewables, that is nuclear, renewables, wind, solar, but also hydro and bio energy, biogas, biomass, biofuels, and also the heat that goes into, when you have a heat pump, you're actually bringing ambient heat into your home, which is very interesting because it's an arrow that doesn't even exist in the Lawrence Livermore Sankey diagrams that all energy wonks like you and me love. And so if you add that together, that's clean energy. Oh, and waste to energy is counted as well. So you take renewables plus waste plus nuclear plus ambient heat, including bio and everything. And that is already, by the way, meeting about just under 1/3 of our needs, right? So you'll get all the people who fall for the primary energy fallacy, Václav Smil, Bjorn Lomborg, Bill Gates, Tony Blair, Dan Yergin, Michael Sembalest, Mark Mills. All of these people think that clean energy is only meeting 20% of global needs because they're obsessed with the production, how much energy we pull out of the ground. But because fossil fuel is differentially so much less efficient than directly producing wind and solar, 17% of electricity, but all of it pretty much is exergy and is used, and hydro as well. And so you've got what you're actually doing is the clean stuff is already meeting just under 1/3 of demand, real demand. So now let's just grow that. And the number I used in my model, 3% faster than demand. So it grows at 5% per year. So you've got demand grows. Let me just back up. The economy grows 3.3. Energy demand grows a little bit less because of energy efficiency on the demand side, grows at 2% per year. And clean energy, starting at just under 1/3, grows at 5% per year.
These are real numbers. Clean energy is increasing at 5%, is it?
How can I put it? They are truthy numbers. I mean, the economic growth and the efficiency are real historic numbers. But when you start to project them out into the future, and by the way, the clean energy growth of 5%, it sounds very low because and I know, solar's going crazy, right? But, this is 5% increased output of not just wind and solar, but also hydro, which grows much more slowly, bio, which grows much more slowly, nuclear, which grows much more slowly, waste, which grows much more slowly. So the average, I've said, is 5%. Now, going forward, all I did in my trivial model was say, well, supposing it just grows at 5%. In reality, as wind and solar become a bigger and bigger relative part of clean electricity, they will dominate the growth rate more and more. So the growth rate will actually grow, but then as they mature, it'll sort of drop away in the out years. Right? But I just made it really simple. I just said, no, this is not a forecast. This is an illustration just to show what happens as long as clean energy grows faster than fossil. And what happens is, the reason that's an important question is, of course, we're doing that right now, and we can continue to do that. And all of our policy could be aligned to do that, to say, look, I don't care what Shell is doing. I don't care what Exxon's doing. I don't care what Saudi Aramco or how much LNG. All I need to care about from a policy perspective is keep clean energy growing 3%. If you can do more faster than energy demand, real demand. And what happens is, for the next decade, you've got incremental energy demand, which is not quite met by clean energy. So 2025 to 2035, energy demand grows, clean energy grows, but fossil stays about flat. And then 2035 to 2045, because of the miracle of compounding growth of clean energy, it just starts to force fossil off the global system. So the fossil then drops by, I think the number is 8% between 2035 and 2045. And then it gets really interesting because that compounding continues. The clean energy continues. Maybe by now it has some, it's 2045. Maybe, who knows? There'll be lots of SMRs, small modular reactors being built. Maybe the first fusion. Who knows? Doesn't matter. As long as it keeps growing by 3% faster than energy demand, then by 2055, fossil fuel is absolutely in trouble. And by 2065, it's gone. Again, not a forecast, just an investigation of it's not even maths, it's arithmetic. And that is what I call thinking like a tortoise, because what you're doing is just saying, I wake up January the 1st every year and I try and grow clean energy by 3% more than energy demand by December 31st. And, of course, you have to, develop the next lot of technologies to keep doing that out into the future. You need a pipeline of technologies or solutions, but it's an incrementalist approach. And by the way, I just think it's politically so much easier because instead of waking up January the 1st and saying, I'm going to demonize Shell. I'm going to stick myself to the doors. I'm going to throw pies at people. I believe that was a big part of your history, right? Instead of that, I'm just going to say, where can we get our 3% faster from this year? Are we on track? Well, let's prepare. Let's make sure we've got 5 years worth of those 3% kind of lined up. Is it heat pumps? Is it those trucks that Michael talked about? What is it that we need to do? Is it reforming, using zonal pricing so we stop switching off those wind turbines in Scotland? What do we need to do? Let's just think about it as barrier busting for very specific target of just using more clean energy of all sorts, any sort. We don't care what sort. So that's kind of the pragmatic approach.
If you're wrong about this, can I throw a pie at you?
Yeah, in 2065.
Okay, when you're 97 or whatever it was.
No, 2065, I'll be 102.
Okay, well,
but you'll have to catch me first. I'm pretty spry.
You'll still be skiing.
I'll still be. I hope so. If I haven't, I used to joke about my preferred way of dying would be to fall in a crevasse aged 100. But I'll shift it back for you. I'll shift it back. I'll do the crevasse thing when I'm 105, and you can pie me if we're not largely, if not. Look, the reality is, joking aside, there'll be a tail of very, very difficult to decarbonize, maybe aviation or shipping you mentioned, and I ducked the question. There'll be a tail of very difficult things. So it won't just die in 2065. But, it will. We should be, to be honest, we should be largely off fossil by then. And I think we will be. This is not just better economics than destroying half of our fossil energy infrastructure in a few years. It's not just better politics because you're not going after the incumbents and demonizing them. I think it's also better. It's in line with thermodynamics because fundamentally, burning stuff is stupid. As I said, if you've got that wonderful electricity from a nuclear power station, you don't make hydrogen that you then have to burn and then have to lose all that energy. But we ought to be not burning stuff for environmental reasons, economic reasons, and also thermodynamic reasons. And I just think that is going to happen. I've said many times in the past, by 2070, somewhere between 2070 and 2100, burning things is just not going to be a thing.
Well, I try to end these podcasts on a pessimistic note, but this is sounding distressingly optimistic, Michael.
I could be wrong.
In which case, I'll pie you. Look, thank you so much. This has been an absolute tour de force. I've learned a huge amount, and I continue to learn a huge amount by listening to your own podcast, Cleaning Up, and also reading your Substack and all of the other stuff that you write and speak. So everyone who's listening to this, do Google Michael Liebreich, and of course keep up with your writings. Do you have a book in the offing or anything like that?
I've only ever written one book. It's called The Complete Skier, and it was actually a how to ski book in 1992 during the Olympic year. That was what I did in the evenings. It was an unbelievable amount of work. I do not know how you do it, churning out a book every year or so. So I've had a book in the offing for 20 years, and I've never got round to doing it. So maybe I need a co-author. Who knows?
I'll be happy to help, and I look forward. Well, if not, I look forward to seeing it in 20 years. Michael, thanks so much. It's been wonderful, and I hope to speak to you again soon.
Thanks very much. It's been a pleasure.
Thanks so much for listening to Saving the World from Bad Ideas, a We Planet podcast. We Planet's a movement of citizens and scientists dedicated to defending the science and solutions we need to save the world. Please do subscribe and share a nice review. It helps us spread the message. We'd also love to hear your feedback and suggestions at our email, podcast@weplanet.org. Please also join our podcast mailing list and we'll let you know when a new episode drops. Just go to savingtheworldfrombadideas.org or weplanet.org/podcast right now. See you next time.